First, I always like to start off thanking Chelsea and her team because they helped set all this up. And as she's mentioned, we've tried to make Making Measurements Matter become a forum that we can use to make these kinds of presentations, to allow people in our community to talk about things, to hopefully treat this as a way to provide both education on new products and on applications. And so, like you said, we're going to do this as a weekly thing. Any of you who are interested, feel free to contact us through that site, and we can help line up a webinar opportunity as well. We try to market out to a fairly large group of people and try to pull people into these things so we can, again, do the things that we're not getting to do right now. Go to conferences, see technical papers. This allows us an opportunity to try to pull this all together now. So today I'm going to talk to you about sampling solutions for volatile liquids. And specifically, we want to talk about sampling light hydrocarbons and other volatile liquids like potentially lean-enriched amines, glycols, things like that. We want to look at this as to how do we properly pull samples, both for spot samples and for composite samples. I'm going to talk about what the differences between those are. Of course, it's going to be a little bit sales and marketing in these things, and so I have to talk a little bit about who we are. And I just realized I don't have my pen so I can draw on the screen. So I'm going to be right back. There we go. That's better. Don't feel comfortable if I don't have that thing in my hand. So I'm going to talk a bit about who we are, who Insight is, and then focus more on talking about automated sampling and composite sampling. Insight Analytical is a Calgary-based company. We're a systems integrator and distributor for other manufacturers. We operate a Northeast Calgary, 20,000 square feet facility, 9 bay doors, 10-ton overhead crane. We can pull a full analyzer building in off the back of a flatbed, drop it off inside, do all the systems integration, and lift it back out again. We're an AB 83 compliant fabricator. For those of you who aren't from Canada, that won't probably be significant, but in Canada, we have a thing called CRN numbers, where we have to have a Canadian registration number for anything that's pressure containing and going into a process facility. And this just means that we're compliant with being able to do that kind of fabrication. We put CRNs on equipment for Alberta, BC, Ontario, Saskatchewan. Personally, I come from a background with a company called Western Research. We developed analyzers for sulfur recovery units, for natural gas processing, and this company has been around for over 50 years now. And a bunch of the people that work here with me have all come from there. So I've had the benefit of bringing in people with a lot of experience in this industry. We have excellent documentation capabilities, and this becomes really important if we're working with large engineering companies on projects. My drafting guy is fantastic and has been doing analyzer drafting and analyzer system drafting for 30 plus years now. And so we do a really good job on the docs packages. I'm really proud of what we do there. We've had compliments from engineering companies. And that's hard to get as compliments from an engineering company usually. All of our electricians are journeyman electrical. We do full CSA on anything, full factory acceptance tests right here in Calgary. Oops, sorry. As I said, we do full systems integration. We'll do everything from little grab sample panels, individual regulators. We did all the sample systems for Coastal Pipeline for TC Energy. We'll do small analyzer panels. This is a little oxygen and dissolved oxygen and water analyzer. We've done dissolved oxygen and hydrocarbons. We'll integrate the sample systems, small sample systems around analyzers. 2, putting together full composite sampler systems. This is one of the things we're going to talk about today is composite sampling. Again, we come with a lot of industry experience, so we come at this pretty honestly. We know how hard it is to do things in the field sometimes. So you'll even notice on one like this, I'd like to point out, we've got a little instruction panel for how you're going to use this device, put right onto the back of the composite sampler. So all the instructions for how to charge the composite sampler, pull a sample off of it, etc., are right there. You'll notice there's a bunch of colored valves down at the bottom. Those are all covered in those instructions. And so when we put a system together, we try to make it to get as operator friendly as we can. So we know lamicoids fall off in the field, they get sun bleached. So we'll do things like color code valves, use different shaped valve handles, so we can make it easy for operators to understand, how am I actually going to use this device? If there's a pattern or a sequence that I have to do things in, we want to make it so it's easy for an operator to follow that sequence when he's pulling a sample. We do analyzers for crude oil blending, or for blending condensate into crude, or butane into crude for vapor pressure control, for sulfur blending. So this is one that's sitting on a crude oil blending skid. We've got crude running through these pipes. They're injecting butane upstream of where we're measuring. We're pulling a small sample off to a little infrared optical bench that's sitting right here, that's connected by fiber optics to an analyzer over here. And we're using that infrared analyzer to do real-time vapor pressure measurements, so we can monitor the vapor pressure of crude as the butane is added in to try to hit pipeline specifications. Oops, yeah, get rid of my ink here. Slides, when I animate these slides, I end up with all kinds of drawings on there. We'll do full analyzer shelters, full sample systems and analyzer shelters. So this is, again, another couple of infrared benches sitting on individual sampling panels. Can't see it over there very easily, but there's some automated grab sampling going on this as well. Full building provided out, dropped in on site, install, commission. This is up at Kiera Simonette, this one. And again, when we do automated sampling panels, we can have multiple cylinders. So in this one, there's 4 floating piston cylinders sitting there waiting to be filled. You can see the actuated valves above and below. We control the entire fill sequence with the PLC that's sitting off to the, I guess as you look at the screen, it's your right. Yeah, off to the right. So we build all the code around it to control that sequence and how those get filled. Again, there's control valve up top, controlling the fast loop through a shelter, Coriolis meter on there, a couple of analyzers tied to this whole thing. And one of my favorite pictures is this one, where that same panel is there, along with 2 composite samplers. We have an automated toluene flush. A lot of times when we're dealing with some of these hydrocarbon liquids, they're really waxy. And so you can get systems that plug and wax off. So we'll build a system in place that we can fill with toluene and back flush the entire system automatically with toluene, clean out the sample system as needed. In this case, we have an infrared analyzer there that we can see a change in how much light's getting transmitted. And that lets us know that, oh, we've probably got some wax buildup in the cell. Let's give it a back purge of toluene. So on the integration side, we're willing to take a look at pretty much any kind of package, large or small. All right, now I want to move on now and talk about sampling hydrocarbons. There's 2 kinds of samples that commonly get taken. One is what we often call a grab sample or a spot sample. And when we do that, we pull that whole sample at once. So imagine if my glass of water was my sample, I walk out to the valve and I say, I want to see what's in my water right now, and I fill this whole glass up. So that sample reflects what's in the process at that moment in time. And it reflects what's in that moment in time, assuming that the sample was collected properly and wasn't biased in any way by how we took our sample. And we want to talk a bit about that, because that's one of the things that we try to deal with when we automate a sample system. The other type of sample that often gets taken is what we refer to as a composite sample. And these are samples that get taken periodically over time. Imagine instead of filling my glass up all at once, I let the water drip in it over the course of a day. What would be in the glass at the end of the day is something that reflected the average of what my water looked like during the course of the day. These often get used for custody transfer. These get used when I want to say, what did that particular plant? I always like to pick on Dale when he's here because I know he's a good sport. Dale's a producer of crude oil, and he's shipping crude oil into my pipeline. I want to know, take a measurement over the course of a day or a week, So what did he give me on average? This lets me know if I take that sample over a period of time, I go, on average, was he on specification? So often this can be done over days or over weeks, or even commonly over months. So when things are going into some of the main pipelines, like Pembina's pipeline to bring things down from Fort Saskatchewan, they'll often do a monthly composite. And that lets them know what value was the product that was shipped to us. We have a unit in with Pembina where they're putting propane onto ships that they ship to Japan. And it takes them about 3.5 days to fill a propane tanker. So the composite sampler fills up over the course of those 3.5 days, taking little bites of fluid as it goes by and filling that cylinder up. So now we have an average of what went onto that ship and know if it was on specification.
Phil, there's a question in the chat.
Oh, cool.
Okay, it's from Bob. How is this different from in situ and extractive?
So, yeah, I mean, I often think of in situ and extractive terms as being used when we're looking at things like stack analysis and things like that, or for analyzers. But we basically, what we do, they are typically extractive systems. So there's a probe or something there that's pulling a sample out of the process pipe, and we fill the vessel out external from the process pipe. You'll rarely see anybody try to take a sample from off of an in situ system, because it would mean you sort of have to be right inside the vessel you're sampling from. There are a couple actually that do that, but the ones that we commonly see on pipelines is always extractive over to the vessel that we're going to fill up.
Phil, before you move on, quick question on the custody transfer. Is that built into the contract between producer and buyer, or is there a larger regulatory board that says, well, you better do it over a day, over a week, over a month?
Good question. There's both. So usually it's a contract between the producer and the supplier that defines kind of what they're going to do and how they're going to do it. But on the natural gas liquid side, so things like propane and crude and condensate, and on the crude side, a lot of this gets covered by Directive 17, Alberta Energy Regulator. So AER has some specifications as well as to how composite sampling is supposed to be done, and how, because again, some of this reflects back to how the tax revenue get generated too. I don't know the value of the product that went through there. So of course there's a government involvement as well. So we commonly do spot samples or grab samples if we want to try to evaluate how a process is running at a certain time and under known conditions. So we'll go out to the field and pull a sample so we can take it back to the lab or to an analytical company that's maybe on site doing testing work for us, and let them make some measurements of how our process is running. And then we can use that data to further optimize our process. So we may pull these sort of so we can get some idea of where we're at and do some process optimization. We may also just want to measure our product quality under known operating conditions. So if I'm running a condensate stabilizer and I'm trying to boil out enough butane to hit to a certain vapor pressure specification or hit to a certain C4 concentration that I'm allowed to put in the pipeline, if I don't have an online analyzer there, I want to go out and pull a sample and see how we're running. There's also types of analyzers that we refer to as inferential analyzers. Things like near-infrared spectrometers, nuclear magnetic resonance analyzers, Raman analyzers. A lot of these things have to build a model in order to predict what's going on in the process. And they build the model by comparing spectra that they measure against known process samples. And so we sometimes are pulling these grab samples so we can help ourselves build these models. So there's a bunch of reasons that we want to do them. When we do these for volatile liquids, for things that are going to bubble fairly easily, we want to make sure that we get, it's always a big deal in our industry, talk about getting a representative sample. We want to get a sample that really gives us representative information about what was in the process. And if I had a water bottle right here, or a bottle of 7-Up right here, and I wanted to measure how much carbon dioxide was in that bottle, well, I'd have to make sure I didn't take the cap off first, because as soon as I let the pressure off, those bubbles are going to escape and I'm going to lose some of that carbon dioxide. So when we want to take samples that we know have dissolved gases in them or that have very high vapor pressure, we want to pull those samples in a way that allows us to ensure that those volatile things, the propanes, the butanes, the H2S, the carbon dioxide, whatever they are, we want to pull those samples in a way that we don't let those gases escape. And there's 2 common methods that we use to do that. We'll either fill what we refer to as a floating piston cylinder, and you won't have to zoom on this because he's pretty big, but floating piston cylinders are basically a steel tube that have a piston inside of them. And what we do is we back pressure one side of it with nitrogen and push that piston right to the top, connect it to the process fluid we want to measure, and then start bleeding that nitrogen out. And slowly, as the process pressure overcomes the nitrogen pressure, it pushes the piston back, but it keeps the whole sample under pressure the whole time. So one common method of pulling those is with what we call either a constant pressure cylinder or a floating piston cylinder. Another common way of doing it is with what we refer to as a glycol displacement cylinder. And we can take one of these, just a normal sample bomb as we see them, a steel sample bomb, fill it up with liquid glycol. We use glycol in Canada. If you're in the US, you can fill it up with water. If you're in the Middle East, you can fill it up with water. Canada, we fill it up with glycol because we don't want it to freeze. But the cylinder is full of glycol. We allow process fluid to connect at one end, open the valve. Process fluid is now pressurizing that glycol. Open the valve at the bottom and slowly bleed the glycol out, measuring how much has come out until this is 80% full with process fluid. And now we've let the back pressure of the valve keep that process fluid under pressure as the cylinder filled. These are often done by hand. It's how guys go out and pull samples out in the field. The issue that happens when we go and talk to a lab, they'll tell us the issues that we have are either the person didn't pull the sample properly. On this one, you opened the valve too fast and it all just sprayed out. So the pressure got a chance to drop and things got to bubble and flash on the way in. Similarly on the floating piston cylinder, he didn't purge the head properly. He didn't do some of the operations in the right order in order to ensure that he gets a good sample. The other thing the lab will complain about is they'll say, the guy might have pulled a good sample, but he didn't write down properly the pressure, the temperature, the operating conditions, where he pulled the sample from, when he pulled the sample, didn't write down the chain of custody information properly. So automating these processes, automating these sampling systems allows us to ensure that things are done in the right order, the right way, and chain of custody information is kept. So the issues that happen with manual sampling is often that the proper sampling procedure isn't followed. Organizations like API, American Petroleum Institute, Gas Processing Association, the GPA, they all write specification documents. Crude oil quality analysis writes a specification document that says this is how you should properly pull one of these samples. A lot of people don't read the manual. They just say, I'll just pull it the way I learned to do it. Joe showed me how to pull a sample 10 years ago. I'm going to go pull it that way. Well, not a lot of people don't pull the sample properly. Then they don't write down the information properly. If you're in a refinery and you're the guy who's supposed to pull the 2 a.m. sample off the bottom of the debutanizer and you're walking by the debutanizer at 1 a.m., you pull a sample and you write it down. That's my 2 a.m. sample. Because that's when you're supposed to pull it, and you were there earlier. So now they go back and try to compare that sample to operating conditions, and they go, geez, it doesn't look anything like the way we thought the debut was running at 2 a.m. because it wasn't a 2 a.m. sample. The other issue we have with manual sampling is we maybe don't have anybody available to pull the sample. Plant goes into upset. I want to pull a sample. Plant's in upset. All the operators and all the technicians are scrambling to try to get the plant out of upset conditions. There's nobody available to go pull that sample. It's middle of the night and nobody's there. We have a customer right now who says, we have people and they're blending butane into their crude and they put it into our pipeline. They know we only come out in the daytime to pull samples, so they make sure they blend on spec during the day. In the middle of the night, they put whatever they want out, and we can't, we have nobody there to pull samples. So if we automate these things, we can actually start to pull samples whenever we want. And if we're using one of those inferential analyzers, we can use the analyzer itself to say, I don't understand the data I'm seeing right now. This stuff's not in my model. I don't know how to interpret this. So I'm going to automatically tell that system to pull a sample that can later be sent to the lab, and it can build out my analyzer model. So when we talk about this, oh, sorry, I skipped a slide here. Skipped one thing I want to show here. This is a sample. This is from one of the lab companies in the States. I apologize to them right now because I always try to mention their name because I stole the video off their website. This is just a sample of them taking some condensate and putting it into a vessel. And, oh, maybe it doesn't want to work anyways. Huh. Let's see. Okay. Well, it's actually a video. It should play a little video where they see when they let the pressure off the condi, it all starts to bubble and foam. And that's what we can't have. We can't have the pressure get let off. So as I mentioned, one of the ways we do that is with a floating piston cylinder. We pre-charge it on the backside with something like nitrogen. So we fill this up with pressurized nitrogen. And we connect it off to the process. And now as we bleed off this nitrogen pressure through a needle valve and a flow meter so we can see how fast it's bleeding away, as that pressure comes off the backside, process fluid pushes this piston down and fills that vessel while making sure that it never gets a chance to phase change. And that's the important thing we don't want to have. We don't want to see any phase change because as soon as we allow bubbles out, those may be the important things that we wanted to measure. And the relevant ASTM standard for filling one of these is D3700. But there's other ones, like I say, from Gas Processing Association and API. So there's a whole procedure, though, under which this should be done. If we just connect it up to a pipeline like this whole line would be full of dead fluid. It's never been purged out. So if we took a sample, we'd get whatever was stuck in those lines. So there's usually a purge valve on the side of these, and we're supposed to open that and let fluid flow out that purge side for a while to clean out all the lines ahead of the vessel. Depending how long they are and what diameter long lines they are, that may take 30 seconds, it may take a minute, it may take 5 minutes. So we want to know how long those are and how long we need to purge and make sure that purge is done properly. Once the purge is done, this valve needs to close. This valve, the valve at the, on the nitrogen side needs to open, and now we can start bleeding off that pressure. We want to bleed it off at a certain rate so we don't fill that vessel too fast and let it start to bubble and flash on the way. So this is what I mean, that if you want some control around this, if you send 3 people out in the field, give them each one of those floating piston cylinders and say, go pull me a sample, they'll each do it differently. One guy goes, I don't want to stand here 5 minutes for the purge, it's cold outside. So he cracks the valve on the purge side, shuts it, and fills his vessel. The other guy says, I don't have to worry about bleeding that nitrogen out slow. I'm just going to crack open that valve and let her rip. So depending on how they pull their sample, they're going to bias the results. On the glycol displacement side, it's similar. We have this whole vessel. We take a standard grab sample vessel like the one I showed you, fill it with water or glycol, something that's denser than the sample that we want to measure, that's immiscible in the sample that we want to measure, and is not a chemical we want to measure. If we're trying to do water and crude, we can't use a water-backed cylinder because we'll get water into our crude as a measurement. So we fill this vessel up with some fluid. Let's say it's glycol. Our process sample up there, the black fluid, is crude oil or something. We open the valve, let the crude oil pressurize that glycol. Now everything's at equalized pressure. We open the bottom valve and slowly start to bleed the glycol out. As we do, the vessel fills over time with crude oil, and it's staying always at constant pressure. So we've kept it at constant pressure, constant temperature, no phase change. Fill that vessel typically to 80%. Remember, this might be a volatile fluid. So now we seal that fluid in and bleed off some more of the glycol to leave a little bit of a gas headspace. The reason we do that is if we took this vessel and we filled it completely with a volatile liquid, like let's say condensate or LPG, and it's filled from top to bottom, and we let it heat up, the liquid is going to expand. And the liquid, when it expands, is going to generate tremendous pressures in there, and that's why there's usually a relief on these things, so that if this thing overpressurizes, you don't actually burst the vessel. So by bleeding some of the glycol out, we can create a gas headspace that when the liquid expands, it just pressurizes the gas headspace a bit. When we get it back to the lab, we push glycol in from the bottom again and compress everything, so any gas that vaporized up here is pushed right back into the liquid again. So we get it back to the same conditions with no gas headspace before we do any kind of measurement. Oops, does this video work on this side? Let's see. No, doesn't. Okay, sorry. Okay. So if we want to do that now, if we want to automate that now, we have to put some kind of controls around it. And so what we do is we build a full PLC package around it, which allows us to start putting all that chain of custody information in. You know, we can put in user configurable stream names. So we can tell people, where am I pulling the sample from? If the PLC is controlling multiple vessels, you know, this is vessel 1 and vessel 2, we might have those connected to different streams. So we know which, and we can put that up, build that all into the code. We've got full documentation of where the sample comes from. If we've got process data, we can be communicating back to the DCS and getting results from pressure transmitters or temperature transmitters, so we know what pressures and temperatures the whole process is running at when we're actually pulling our sample. If we know some other process conditions, like some component values, we've got an infrared analyzer there or something like that, we can display that data as well. We can have all kinds of alarms, analytical results, operational maintenance status, all of that built into the PLC. So now everything's going to be controlled by that PLC. All the data that we need is available to that PLC. An operator can go out and look at it and go, oh, this one's full already, this one's empty, and he can see the conditions. And if he wants to pull a sample while he's there, push a button and say, pull a sample. But more importantly, someone in the control room can say, I would like to get a sample right now, push a button at the control room, send a signal from the DCS over to the PLC and say, we're going to take a sample right now. Or we can even have this set up so a cell phone can log into a SCADA system and say, I need a sample at this moment. So we can put all of this under PLC control. We can control all the things about the cylinder fills, how fast we're going to allow them to happen, whether a cylinder status is present or has been removed, whether that cylinder is available to be filled. We can trigger it from a bunch of different conditions. We can put permissives in there to say, well, you're not allowed to actually do a fill unless the flow meter is reading over 20 deciliters a minute, because I want to know how much flow I've got going through the system when I pull a sample. Am I pulling an actual flowing process sample?
Phil, we got a question here on
sure.
the chat here. It's coming from Mike Strobel. What is the typical pressure differences between the nitrogen charge and the process fluid in the piston samplers?
Strobes, how you doing? Hi, Mike. Yeah, it's usually we look at what the maximum process pressure they expect to have and put the nitrogen pressure 10% over that. So if they say, you know, normally our pipeline runs at 100 here in the States, so we'll use those funny units, 100 PSI, but our maximum pressure is 150 PSI, we'll pressurize a cylinder up often to 165 or 180 PSI. So that way the nitrogen back pressure is more than the process pressure. Then we can start to bleed the nitrogen off, have a pressure transmitter on the process side on the nitrogen side and say, oh, the nitrogen pressure has just dropped down to the process pressure, so this thing should be starting to fill now. So that's how we know when it should be starting to fill. And I'll talk a little bit later about how we use sensors to determine is the piston actually moving, and did we get a proper fill or not. So answer everything you need, Mike? Okay.
Yes, you did. Thanks, Phil.
Yeah, no worries, Wayne. And of course, because again, since we're putting all that into a PLC, now we have all that chain of custody information. We know when it was pulled, we know what flowing process conditions were when it was pulled, and all the things that the lab is going to need in order to take that data and make it be into something useful that we can use for either providing feedback to operations on how they were running at the time, or for chain of or for custody transfer information. If we are doing this with a floating piston cylinder, we add in this piston sensing devices. So the specification, ASTM D3700 says you're only supposed to fill the piston 80% full. So we put a magnetic sensor, we put a magnet in the piston, a magnetic sensor at the top, and a magnetic sensor at the 80%. So we know if the piston is up at the top, that piston hasn't been filled at all yet. We open the system up, we initiate the fill, we see when the pressure of the nitrogen drops below the pressure of the process, and we know when that happens, that's when the piston should start to move. So we watch then on the PLC, did the piston start to move? If not, maybe it's stuck and we're gonna give an alarm saying we got a false fill going on here. Or we watch and we see that piston move down until it hits the 80% magnetic sensor, and that says stop bleeding off any more nitrogen. That piston is full enough now. So again, we can put all of this under PLC control and fill this exactly to the way a set of standards or guidelines says it's supposed to be done. We also provide complete error tracking diagnostics, and so we can customize all these controls for different applications. One of the ones which has come up a lot now has been truck loading and offloading. People saying, well, I want to know when that I'm buying propane from Dale, and I know Dale's a shiesty character. So when a truck comes in from his plant, I want my PLC to say, the operator of the truck had to say what plant he was from. When he starts to offload, I'm going to pull a sample from Dale's trucks, because I want to see if Dale's actually shipping me on spec product. So, or I could say I'm going to pull a sample from every truck that comes through the bays. Or when we talk about composite sampling, I can say I can fill a cylinder just part way based on Dale's truck and average over the month all the trucks that Dale sends me. So there's ways we can do this as both a grab sample and as a composite sample. So we can put these into full panels like this one, I showed in the picture earlier. This was going to go in an analyzer building, so you'll see that it has a large control valve up here. This was controlling the fast loop. It had an inferential analyzer. This is an infrared analyzer bench sitting down here. I choose a different color on my pen. And over here are my 4 pistons waiting to be filled. So these allow us to pull grab samples whenever we want, PLC to control the whole thing. So if the analyzer sees off-spec product, if the analyzer sees a product that it doesn't understand, it can say, I want to fill a sample right now. Or if the end user says, I want to check and see if that analyzer is reading right. Right now it says I'm at 4% butane. I'm going to pull a sample, send it over to the lab, and the lab can tell me whether the analyzer was reading correctly. Big benefits are that we can trigger it remotely, pull the sample the same way each time, and there's no need to physically handle any of these samples. The only thing an operator does is put an empty cylinder into the rack, once it's in the rack and it's connected to its quick connect system, which can isolate it, it's connected to other valves, opens the valves on the cylinder and he walks away. When he comes back to take a sample out, the only thing he has to do is close the valves on the cylinder. All the other valves have been controlled under the PLC control. Quick connects are there to protect it from any other leakage around the valve. Close the 2 valves and take the cylinder out. It's relevant because there's been situations when people are sampling things like LPGs, liquefied or propane. They start filling the cylinder. If they overfill it, the propane starts to blow out. It flashes and it gets really cold. So guys will have gotten, basically frostbite on parts of their body because of the fact that they haven't closed the valves properly. So we do this as well because there's an HS&E advantage. And certainly if you're starting to talk about pulling samples that have high levels of H2S or high levels of other toxic chemicals, putting an automated system in there provides us a way to protect our operators. Of course, a big panel like this with all the bells and whistles on it is going to look expensive. We'll do these as much smaller panels as well. This was one that'll just have 4 floating piston cylinders on it. Doesn't have all the fast loop, doesn't have all the analyzer stuff. It's basically just floating piston cylinders. Again, we have a client who's looking for one who's just one cylinder. It says, I want to be able to pull a sample off my pipeline in the middle of the night and find out if that guy's blending off spec or not. I just need one sample. So we'll do as many cylinders as necessary. We can build in triggering capabilities from the DCS, from any other remote system, local control. We can do these with all electric actuation, all pneumatic actuation, full date and time logs of the PLC, interface it to any online analyzer, even your gas chromatograph. You have an online GC and you say, boy, I'd like to take a sample once in a while and check and see how that GC is doing. This lets us date and time stamp things. We can have data from the GC feeding into the PLC. So we know what the GC was reading, when the lab sample was taken, and then we get what the lab results are. So this provides us a means for reliable, repeatable grab sampling, full chain of custody, no human intervention. Typical applications we've seen have just been process grab sampling from NGLs. This could be C3 plus streams, C5 plus streams. Guys, you say, I just want to be able to take a process sample and have a lab guy show up and pick up the sample and take it to the lab and analyze it. Truck rail loading and offloading. Sample trucks, as they're loaded or offloaded. We want to know what product did we put on there. Do we put the right product in? We have a client out in Ontario who puts propane and butane to cavern. Before he unloads a truck, he wants to say, I got to pull a sample and make sure I've got the right material going off to that cavern. I don't want to put butane into my propane cavern. Grab sampling during crude oil or condensate blending operations. Again, if we're going to run 24/7 blending skids, we might want to be able to pull samples day and night and not necessarily have operators have to go out there and get them. Other samples we can consider are things that are just difficult to sample, rich and lean amines, things that have high amounts of H2S in them. Anything that we're worried about gases evolving from, we want to look at putting some kind of way of keeping that fluid under pressure. So things like amines and glycols. And then we can tie this into any inferential analyzer. FTIR is in a refinery doing gasoline blending. And you say, well, I want to be able to pull samples whenever I need to. Hook this up, connect it to your FTIR. FTIR goes into fault, says pulls the sample right away. So that's all about grab sampling. This is one point in time. Next, we're going to talk a bit about composites. So composite sampling is done to give a time or a volume proportional sample that's acquired over a period of time. So we call it time proportional or volume proportional because either we say every 15 minutes, put a shot into this vessel. Every 15 minutes, put another weight onto the scale. Or for every 50 weights that go by, volume proportional, for every 50 barrels that goes by of crude oil, put a milliliter into this glass of water, into this cup, and let the cup fill up over a period of time. Now it's going to give me the average on a flow weighted basis of what will flow by in that pipeline. So the composite sample represents the average of the process fluid or the flowing fluid over a period of time. And we use this to say, on average, did the product that I purchased, did it meet my specification? And what was the value of that product? If I'm buying crude oil has or a condensate, for example, condensate has a difference in price based on its density, based on its sulfur content, based on its vapor pressure. So there can be different specifications. I want to know, based on over time, on an average over time, the stuff that Dale sold me in the pipeline, what was his stuff worth? The composite sample also, if you read API 14.2, they talk about the statistics of composite sampling and how the more samples you put in, the better average you get. You could imagine if I wanted to know what Dale shipped me over a month, I could pull one of those grab samples every day and just average those 30 samples. That's going to give me a certain statistical spread. Each one of those individual samples, I'd have to measure it individually. Every time I do that measurement, it has some errors. So I've tried to make an analogy to that, to saying, I've got a scale and it's used to measure gram wafers of gold, 1 gram wafers. And each one of those wafers is slightly different in weight. And every time I make a measurement, the scale has a bit of error as well. So when I put these guys on the scale, I get a different weight than the true weight of the gram. I put a 1 gram one on there, it might weigh 1.001. Put another 1 gram on there, it might weigh 0.999. And some of that is the error of the scale. If I average all those individual numbers up, I'll get to a certain error number, which might be, well, if there's not a large number of samples, it can be very large, fairly large. A better way, if I wanted to get the average weight of those gram wafers, would be to put 10 of them on the scale all at the same time, take one measurement, and then I divide the error of that one measurement by 10. So typically, if I take a lot of samples, average all those samples out together before I make a measurement, I'll get a better, more precise number than if I try to take a bunch of individual samples and average their results. Statistics talks about the error in the mean is bigger than the mean of the errors. So anyways, it's mathematically it works out, and API 14.2 goes all over this. So when we're doing composite sampling for a pipeline, they want to take a pretty big sample typically. So a composite sampler will have this large accumulation vessel. You know, a typical one that we'll do is like a 15-liter vessel. And we fill that vessel up over an hour, over time. Right now in Alberta, the Industry Measurement Group, which is a bunch of measurement-oriented persons from the oil and gas community, are meeting and revising these best practices for composite sampling. Dale was asking about it, you know, is it plant and pipeline operator specific, or is there some other governmental regulations in there? Well, the Alberta Energy Regulator is saying we'd like to get a standard together for so that everybody does composite sampling the same way. Right now, the standards aren't that great, and they vary depending on the size of the facility, so we want to make something that makes it very clear for how you're supposed to do this. That committee is being represented by Pembina Pipelines, Keyera, Secure, Jarrett Torres from Secure is running that committee, CNRL, a bunch of the other oil and gas guys here. A couple of the relevant reference standards are API 8.2, standard practices for automatic sampling of petroleum products, and the Alberta Energy Regulators Directive 17, Chapter 8. We want to talk a little bit about how these work. Ink color here. So the way these usually work, simplified sort of version of it, is we have flow going down a pipeline over here. We've got a probe that can extract a sample, and we've got a small pump here. This pump is not continuously operating. It's a one-shot pump. Give it a shot of air, and it says, I'm going to inject one stroke. So most of the time, there's nothing happening, and fluid is flowing along down this pipeline. And then some type of a control system says, okay, I would like you now to open this valve and take a shot with the pump. The pump pushes a small amount of fluid over towards this accumulator. So the pump stroke might be set to deliver 1 milliliter. This might be a 15-liter cylinder. So we could slowly fill that cylinder up by putting a whole bunch of 1 milliliter shots into it. And they might say for every 10 barrels of crude oil that goes by, put a milliliter shot into that accumulation vessel and let it fill up over time. This vessel is another floating piston type device. So it's got a piston inside of it. I'm going to show a detailed drawing of one of these in a few slides from now. So it starts out with the piston right down at the bottom, and as the pump pushes things in, it pushes, the fluid pushes the piston up, and it pushes it up against some back pressure. So the accumulator vessel is kept pressurized, no liquids or no vapors are lost, there's no gas headspace, and we just slowly fill this vessel up over time. The main parts of a composite sampling system are the accumulator vessel itself. This is where the fluid actually goes. This is the pre-charged cylinder, is the back pressure gas. Oops. API 14.2 says there's got to be a continuous measurement of level. So there's a level transmitter there that says how full is that cylinder. Because this accumulator is so big, 15 liters, it's made of steel, it's really heavy. You're not taking it out to take it to the lab. So there's got to be, or there should be a way to pull a lab grab sample off. And you'll see over here, what we've got is another one of those floating piston cylinders that's hooked up through this valve assembly down here. So we can pull a sample off of this cylinder when we need it. I'm going to talk about the process by which that happens, again, in a few slides from now. This operational valve assembly is how we control everything. Injection pump, not shown on here, something to put it in there, and a thing called the mixing valve right here that I'll talk about in a minute as well. So the interesting thing, the relevant thing, the sales pitchy side of thing I'll mention is that we were approached by a major producer who said, in Canada especially, we can't get composite samplers that have full CRNs and meet all of our specifications and requirements and can be customized. So we had the pleasure, the honor, and the opportunity to work with a major producer, say, we're going to design you a customized composite sampler that meets all your needs, meets everything in API 14.2, meets everything that Directive 17 wants, and makes it easy for people to use and can be customized. So part of this whole system starts with the probe. And a probe is always recommended when we want to get a representative sample. We'd like to get a sample from the central third of a flowing pipe. That's where things are best mixed. That's where things are usually most relevant of the process fluid. As we go near the walls, that's where more contamination builds up, and that's where we're less likely to get a good sample. So we put a probe in and we try to sample from the central third of the pipe. We also want to be sure that whatever's in that pipe is well mixed. So upstream of this, we may well want to see something like some mixing veins, so what we refer to sometimes as a static mixer, so that the fluid have to flow around these things and mix. There's also things like cojet mixers, but we want that fluid that's in the pipe to be well mixed. If we grab a spot sample, and people see this especially in stack gas analysis, depending on where you put your probe in the stack, you can get a different number because you have stratification and you have flow variations across the stack diameter. Same thing happens in a flowing pipeline. Even worse, if we're trying to do measurements like water and crude, the water is going to want to tend to build up down at the bottom of the pipe. So if I just sample from the top of the pipe, I'll almost never see water and crude oil. If I sample off the bottom of the pipe, I'll say there's a lot of water in that crude oil. So what I want to put upstream of my sample point is a mixing device, a static mixer, a couple of veins that it has to flow around, something that makes it spiral as it goes around. So the water that's near the bottom gets kicked up into the main flow, and we get a sample that represents the entire process fluid. To do that really well, we may also have to include what we call isokinetic sampling. So we may have to try to ensure that whatever the velocity is for the process fluid, we sample with the same velocity going up the pipe. It's the ideal situation or the ideal case to do. It requires a little bit more complexity on the pumping side, and so I'm not going to cover that too much here. But if anybody wants to talk about why we isokinetic sample, pull up as a question or something like that, and I'm certainly happy to discuss it. So for the composite sampler, in normal operation, stuff slowing down that process pipe, there's a probe sitting there. There's a pump that's just up near the top here, and there's a continuous fast loop. Process fluid is coming out and following that red line, flowing past that pump, and there's some kind of sample return point. It may be a low pressure sample return in a process, it may be across a process pump, but there's something keeping continuous flow that goes through that loop, that goes up near where that object is. It's labeled P-1141. That's our little injection pump that's going to push things into the composite sampling vessel. As the right number of barrels go by, we may want to actuate that pump. So we'll talk a little bit about what that pump actually looks like. Oh, and I've got notes from an old slide on here. Yeah, 1 second, I'm just going to delete some stuff here. Yeah, keep this. 1 second, we're going to fix some stuff up. Looks like I didn't delete everything off of the previous time I used this presentation. Yeah, you can see me fix things for a while then. There we go. So back to here. So the sampling pump's usually mounted external to where the composite sampler is. And you can see down here, there's a 1/2 inch or a 3/4 inch. No, didn't delete everything. Oh, well. I always screw something up when I do one of these. That's why I do them so often, so I can get enough practice. There's gonna be bypass flow running through that cross underneath there. The pump injection point is right here. So this screw that's up at the top allows us to adjust the injection volume. That's gonna say how big of a volume do I want per injection. I want 1 milliliter. I set that screw to give me my injection volume. The volume is determined by how many injections we've decided we want to use to fill up the vessel. I want to use 5,000 injections to fill up this vessel. And how big is my vessel? 10 liters. 5,000 1.5 milliliter injections would get me to 75% full. That's probably pretty good. And what this pump does is when the air actuation hits, it does 1 stroke of the pump, sort of like you can imagine a piston going boom, sucking some in, pushing it out, and it pushes 1 milliliter out, or whatever my pump stroke is set, out this side. And that's going to go over to my accumulator vessel. This guy still has notes on him as well. The accumulating vessel has a floating piston in it that you see right here. That when we are getting ready to use this vessel, we put nitrogen pressure above this piston that's up here in the stand that goes above the accumulator, and it pushes that piston right down to the bottom. Just gonna clean this slide off as well. 1 second. Not sure if these are all about this now. Oops. Just can't take all this stuff. So when we want to start, we push the piston all the way down to the bottom. I'm going to talk about what that central guy is in there in a minute. We push that piston all the way down to the bottom, and we're going to fill him from the bottom as well. So our fill is going to come in from here. So initially that piston is right down here. We push process fluid in to push that piston up. That raises the piston against the nitrogen pressure that's pushing it on the other side. This piece that's in here can also be actuated and moved based on a piston that's above it. And I call it the French press because it looks like a coffee French press kind of. But what it is a plate that they can move up and down to mix the stuff that's inside the cylinder. Again, if there was 2 different density fluids in there, one would settle to the bottom. So what we want to be able to do is mix the fluid that's inside there before we sample from it. So when we want to fill this accumulator, what we do is the sample pushes small individual aliquots of fluid over to that accumulation vessel. So now you can see the line that's in red. The line that's in blue is the air coming down to actuate that little pump. The lines in red are full of process fluid. So we've had our continuous fast loop flow going down to that sample return pump section. But now the pump is pushing red fluid over to V-1142. That's our accumulator vessel over on the right. You'll notice the lines are marked that they have to have a slope. Another important part of API 14.2. If you want to do water and crude oil or water in your condensate, sorry, my backdrop went off. If you want to do water and condensate, water's denser and it's going to settle out and sit in a low spot. So all the lines have to be designed to slope over to where the accumulator vessel is. And that way you'll not leave a low spot that can pool up with water. So the accumulator has to have a level gauge, both a visual indication of level that we see right here. So we have a set of magnetic flaps that'll flip as a piston moves by it. And we also have a level transmitter up here that allows us to continuously measure the level. Again, API 14.2 says, you got to understand what your piston strokes are. You set it to push 1 milliliter a stroke. After 1,000 strokes, it should have pushed a liter. That should have changed the level by this much. So we want to get feedback on that. Is it actually filling the cylinder up properly? Before we pull a sample off for lab analysis, we want to make sure it's well mixed. So this comes back to that French press thing again. We have the ability to inject nitrogen pressure on top of this piston assembly up here. If we put pressure up there, it pushes that assembly down and it pushes the French press down. If we inject nitrogen on this side, it puts nitrogen pressure here and it pushes that piston up and it pulls the French press back up again. So we have a thing over here at the bottom that we refer to as the mixing control valve. See, it has a little joystick on it and 2 breather ports. That's for the air to get released. And the joystick says, push the piston down or push the press down, pull the press up. And so an operator, before he's going to pull a sample, is supposed to take that joystick and move it back and forth 6 to 8 times. API 8.2 says 6. When he's doing that, what it's doing is changing again. You see these blue lines. The light blue one is the one that's going to pull the piston back up again. The light blue one comes over. I think you can, let me see if I can put a laser pointer on here. Oops. Oh, I can't. Okay, the light blue line is actually to push that raises the French press back up again. The dark blue line, when it's actuated, when instrument air is there, it pushes the French press down. So this lets us move that thing up and down several times and mix that cylinder appropriately. Sorry, I'm running a little bit late here on time. Not too many more slides. We want to be able to pull a lab sample off. So we set this up so we can have a lab sample cylinder sitting off to the side of it, ready to take a sample off to the lab. And again, we go through a bunch of things to check to make sure we have double block and bleed on everything in case we have volatile or hazardous fluids in there. So everything's prepared to be able to be bled off. This can all be done safely. Again, color coding valve assemblies to make it easier for operators to do things.
Phil, we have another question here.
Yep.
Assume that the testing and calibration is based on mechanical performance.
Yep.
Testing medium. What is the typical FAT based on certified documentation requirements? Usually
based on just on a lot of pressure certification stuff, hydrostatic testing, making sure everything's pressure certified. The big thing usually comes out to doing an SAT test as well, or a site acceptance test, where we actually say, okay, we're going to do things like water injection in your pipeline and see that we actually get water in our sample at the appropriate amount. Or we'll close a loop someplace. If we've got a recirculation loop, we'll close the loop so we know what fluid is in there and see that we pull the sample, measure that the level's moving appropriately. We do it at the factory acceptance test. We measure, does the cylinder move appropriately or does it fill appropriately based on the size of injections? If you're interested, we have a full FAT procedure that we run through with these. Again, like I say, color coding valves just makes it easier for operators. A few different things on pulling the lab sample, similar to our automated grab sampling. We want to do this in the right order. So the first thing we do is run it in bypass mode. Our sample is now moving through that red line and bleeding out just the head of the cylinder, but the green line isn't actually bleeding anything away yet, so we're not bleeding nitrogen pressure off. It lets us purge the head of the cylinder. And then when we go to fill, we close the valve on the bleed side, and that starts to push the cylinder head back, and we actually fill that whole cylinder up under pressure. So in summary, composite samplers let us provide a solution for pipelines, for ship loading, for truck loading, where we can get an average sample that's taken over a period of time. We can provide the full package to do that, from fast loop pumps, sampler shelters and buildings to the samplers itself. As far as Inside Analytical, we represent a number of other technologies. I talked about these infrared analyzers, JP3 measurements. We use Z-gas for hydrocarbon and water dew points, spectra sensors for trace components like H2S, barb and oxygen analyzers in both water and gas phase applications, especially VRUs and flare gas, reflux samplers for the petrochem industry. We've recently brought on the whole Hawk measurement line as well, which allows us to do multiple different things, from flow measurements level measurements with ultrasonic, fiber optic integrity measurements, so we can go on 40 kilometers of pipeline and say where you have a leak based on how the fiber optic itself we shoot a laser down the fiber and look at backscatter off the fiber. We can tell you the temperature, the strain, and if there's vibration on the fiber. So we can use that on conveyor belts for looking for vibration. We use it on pipelines for looking for the vibration and the temperature cooling that happens when you get a leak. And we're going to do, Scotty, when were we planning? About 10 days from now, I think we're going to do a webinar on fiber optic sensing.
Wednesday, August 19th.
Cool. Yeah. We use guided radar, which we can use in high temperature bitumen tanks. We use these in a lot of places. We just did an application for guys that are making wood chips and wood pellets. Tailings ponds, we use a sonar type device. We can tell you the pond, where the pond bottom is, and also the layer that occurs where it hasn't fully settled out yet, but you have kind of this viscous layer in between the two. So we can get multiple levels in something like a tailings pond. Simpler ones, just a simple acoustic type sensor for relatively simple applications. Feeders, we can look for, use a gladiator across a conveyor belt, or a system where we want to see if we have like a block chute, whether we have things like bitumen blocking our chute, we can't move things anymore, to free space radar that can shoot down through narrow ports. So again, we can pick up things behind a grill or a grate. And fly ash hoppers, a bunch of different technologies for level measurement. The fiber optic one is especially interesting. It uses 3 types of spectroscopic backscatter and tells us basically the strain in the pipe, the temperature, and whether there's vibration. So we can use this on, we're doing an application with Tech Kaminko on a conveyor belt, and they want to know, are my bearings overheating on my conveyor belt? Run fiber along the whole conveyor belt, we can tell you where the hot spots are. So that's a bit of my sales pitch. The last piece of it is just a little bit of animation of some of the stuff that we integrated. As I wrap this up, I just want to say that, we try to be a value-added solution provider. We try to understand our customer applications, build things customized to the systems that they want to see done and to the application that they want to do. I've got a pretty great staff. Most of us come from either engineering technologists, engineers, scientists. We're a largely technically focused company with, of course, some sales arm because we've got to get our product out there. But what we're really out there is to try to help you find a solution to what you need to get done. So with that, I'm going to wrap it up and say we're primarily measurement guys. We've been very Western Canadian centric. Got a strong service group out of Grand Prairie and out of Edmonton, out of Calgary. analyzer, sample system, and shelter design team. I teach courses on sample systems all over the world. Well, used to do them all over the world. Now I get to do them in front of a camera like this to people all over the world. And we're happy implementing solutions like this for clients across North America. Final thanks out to Making Measurements Matter in Chelsea, and some contact info at the end. Now I'll wrap it up, and sorry I'm about 7 minutes late. So thanks all for coming. Any questions? Happy to try to address those.
Hey, Phil, you're using me as an example of a dodgy producer. There is a nice segue to my question here. So back when I was operating a gazillion years ago and with emissions monitoring, our only concern was stack top temperature. And the first thing I learned was to turn off the chart recorder if the incinerator ever went out, because it just locked into that temperature. Now, do you see, now of course these days you've got full data acquisition systems for emission monitoring. Do you see DAS being used for custody transfer with these samplers?
There's guys who've talked about putting them in. So we do have a couple of places where we put analyzers in, and they're doing continuous online analyzers instead of sampling and putting that onto a DAS system. But yeah, they are bringing a lot more. And that's where we think that putting in the automated side of it, because now, just like you said, you know, if I'm producing an off-spec product for a while, well, maybe I'll just tweak with the flow rates and make sure I don't have as much volume for a while. So now when you put a DAS system around there and you acquire all that data, you can look for things like that a lot more easily, right?
Yeah, exactly.
Yeah, so we are seeing more data acquisition, and that's one of the things we're doing is trying to pull a lot more data together. So when you're doing that custody transfer information, you've got all those numbers.
Yeah, I'm just speaking as a former operator, and we're very clever at working the system.
Oh, yeah. Well, that's the other thing that, you know, like for these, I put Chris's email wrong in there. I used to do that to Scott all the time. The other thing is that guys were doing things where, like for a truck offload, they'd say, well, I'll take one sample a month. So I'll pull one grab sample. I'll go out to the plant. I'll go to where I'll pick on Kira Simonette. I'll go out to Kira Simonette, pull a sample of their LPG on the first Tuesday of the month. That's going to be what I'm going to say Kira Simonette truck to me all month. So on that first Tuesday of the month, you make the best, most valuable product you can when the guy's going to pull the sample. Exactly. And then that's what you're going to get paid for all month. So now instead we can say, okay, well, what we can do is pull multiple samples. We can randomize when those occur, do all sorts of things to try to avoid that potential for people intentionally introducing bias.
Right. Okay.
Cool. Thanks, Dale. Anything else? If not, thank everybody for coming. You can expect to see probably an email out from us, which will have some information about some of the products we talked about here today, and maybe some information also about some upcoming webinars as well. So again, thank you all for your time. Apologize for running a little bit over, and hope to see you all again soon. Thanks much. Was that a question? Oh yeah, there's this, yeah, from Surya. Cool, thanks Surya. Yeah, Surya just put a comment I saw in the all chat as well, just saying that, yeah, refineries use these composite samplers all the time, see what their product averaging is like. So we see the same thing now in gas plants. Cool, thanks everyone. I'm gonna shut this meeting down.